Hi everyone. So in this video, I'm going to go over how we could count the number of spanning trees of a given graph. So this is kind of a fun exercise. If you have an interesting graph and you want to see how many different ways can you find one of these spanning trees. So let's take a look at this graph. Oops, as a starting point. So, of course, if you have a tree to start with, there's only one spanning tree of that tree, and that's the tree itself. So we're going to look at graphs that don't that are not trees, and we'll see if we can find some spanning trees of them. Now, the first thing I want to calculate here before I get started is the redundancy of this graph, because that gives you an idea of how hard the problem is. So let's just count. We have 1, 2, 3, 4, 5, 6, 7, 8 vertices. So I'm going to count 8 vertices. And if I count the number of edges, I've got 1, 2, 3, 4, 5, 6, 7, 8 edges as well. So m equaling 8. So the redundancy of this graph is m minus n minus 1, which is 8 minus 8 minus 1, which is 8 minus 7, which is 1. So this, if it were 0, it would be a tree. So this is sort of one more level of complexity, say, than a tree. Now, how are we going to find spanning trees? Well, there's a lot of different ways to do it, and we talked a little bit in a previous video about one way, which is just start trying to connect to edges. But I'm going to give a different way in this video, and that is to say, I my spanning tree, if I have a spanning tree, I know it must be a tree. So in particular, if I look at all of the edges, like these edges, that are in fact bridges, that would, if I remove them, they would disconnect the graph, those must be in any spanning tree that I might find. And the reason is if they weren't, then I would have a disconnected graph. So I'm going to go ahead and make sure that these guys stay in the graph. So now I have some choices here. And uh, the choices are, you can think of the choices that of which edges to add, or you can look and identify that what I'm left with here is a single cycle. So I have one cycle now that's sitting in the middle of my graph. And it turns out, if you think about it, that none of the edges on that cycle are bridges, because if I remove them, I stay connected. So in fact, what I can do is I could remove any one of these edges and get a spanning tree. So let's just see what that looks like. So I have 1, 2, 3, 4, 5 edges. So let's go ahead and duplicate this and move it over a tad 5 times. So let's see, 1, 2. This is going to get a little messy if I'm not careful. So let me separate off my original graph. So good. Okay, great. 3. And I'm going to probably run out of room without moving one of these over a tad. Okay, I'm going to move my second examples down a bit so that I have room. Okay, one more. Let's see what we get here. Great. Sorry, guys. Let's move this whole thing down a bit. That way I'm not bumping up against my data here. All right. So we can see all of the just 5 copies of this graph. And what I want to do is I'm just going to remove one of these edges in each of the copies, but a different one. And I contend that when I do that, no matter what I do, I'm going to be left with a spanning tree. So let's take a look. In this case, you can see, yes, it's a tree. If we, oops, so in each of these cases, you can check quite easily that you have a tree. And the reason that you have a tree, I mean, what's the underlying idea here? The underlying idea is when you remove one of those non-bridges, you're staying connected as a graph. And so you can always there's always a spanning tree. And so you're reducing the number of edges essentially. And if you look over at our redundancy is sort of the excess number of edges beyond the n minus 1. But since you're not disconnecting the graph, you're going to eventually, I mean, in this case, just by removing one, you'll get down to 7 edges and it's still connected. And that's all you need to be a tree. You need the n minus 1 edge condition, namely that there are 7 edges in this case, um, and and that it's connected. So since it's not a bridge, you remove it, it's still connected. Okay, great. And and of course, these have to be all of them because we couldn't remove more than one. Then we would get n minus 2 edges and we would have disconnected it. So these are, each one of these are spanning trees. I think I colored this slightly wrong. All right. So in this case, we get 5 different spanning trees for this graph. And I want to say this, you could have changed this problem by actually just moving this AF edge to be FG. Then you would get 6 because you would have a cycle with 6 of length 6. So it's not just that you have, I mean, you're not getting this number of them just because you have a single cycle. It's the actual cycle that you're dealing with that tells you you have 5. All right. So let's look at another example where maybe things get slightly more interesting, but the same idea applies. Okay, I'm going to bring this down and focus on this example here. Okay, great. So let's count again. We're gonna use redundancy as sort of the thing to look for when you're trying to make these computations. So in this case, we have, let's see, 1, 2, 3, 4, 5, 6, 7, 7 different vertices. So n equals 7 here. And how many edges do we have? Well, let's count. We have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 edges. And then thus our redundancy R is, which is m, let's recall the formula, m minus n minus 1 is equal to 8 minus 7 minus 1, which equals 8 minus 6, which equals 2. So 2 is one more than 1. So we would expect this to be maybe one more level slightly more complicated than the last case. But in some ways, it's not too bad. And the idea here again is to remove things that are not bridges, but also to keep things that are bridges. You can't remove a bridge and expect to get a spanning tree because um, those bridges connect all your nodes. So I've highlighted the only bridge that exists here, but then we can see that we have one circuit here and we have another circuit here. So what I want to say is that if you remove any any edge or link from from both of these circuits, you will get a spanning tree. And why is that? Well, if I remove a link or an edge here, and I remove an edge here, then that takes this m from 8 to 6. It reduces m by 2. But that will take this redundancy and it will also lower it by 2. You'll get 0. In other words, you will get n minus 1 edges. 7 minus 1 is 6. 8 minus 2 is 6. You will get exactly the n minus 1 edge condition. And since removing anything here, any edge here will maintain the connectivity of your network, you will have a connected network, well, or a connected graph with n minus 1 edges, which means it's a tree. So, how do we count how many ways we can do that? Well, the point is you have three edges here that can be removed. In other words, you can remove any one of three edges. So maybe I should write that instead of three edges can be removed. It's a little misleading. So let me change what I wrote here and just say any one of the three edges, and let's write them down, EF, EG, and FG can be removed. And likewise, any one of the four edges, AB, BC, CD, and DA can be removed. And then you'll get a spanning tree. So how many choices do you have in total? Well, you have 3 on the right-hand circuit and 4 on the left. So those two will multiply to give you the total. And the way you can think of that is if you remove this, then you have 4 choices. That's 4. If you remove this, you have 4 more choices. And if you remove this, you have another 4 choices. So that gives you 3 times 4. And so these two observations reveal that there are 3 times 4 equaling 12 possible spanning trees. So, this graph. Now I'll say this. I mean, it's of the graph or of this network. Okay, great. Now let's take a look at one more example here, and then we'll look for another pattern. Oops. So if you have a graph like this, we can check, and again, let's check the redundancy. The redundancy is a good guide of complexity. And as we're seeing, it tells us how many edges we can remove. So let's see, we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we have 8, n equals 8. M, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So m is going to equal 9. Redundancy equals m minus n minus 1, which is 9, minus 8 minus 1, which is 9 minus 7, which again is 2. So we're in a similar situation here. We have redundancy 2, meaning we should be able to remove 2 edges from this graph. However, there is a bit of a difference here from the prior example. From the prior example, we could isolate sort of two circuits that were sort of disconnected. Here you have a circuit like this, but then the other circuit is not sort of a disconnected thing, it sort of overlaps. So we have two circuits that sort of overlap in a way. And that may make things a little less obvious on how to do it. Um, Nonetheless, you can certainly include your one bridge here that needs to stay in the graph. And then there's a question of I want to be able to remove two edges. Okay, so which edges can I remove here? Well, I contend that if you remove um, any of these edges up here, this edge, this edge, this edge, this edge, that uh, you can remove any other edge. Okay, so what am I saying here? So what one can do then, when they see that they have these two different circuits, is you have to make a choice of the different possibilities here. So let's take a look. I'm going to copy this and take a look at the smaller of the two circuits. So I have this circuit here. And what I know is I'm not going to be able to keep that whole circuit because the spanning tree must not have any circuits. So I'll have to remove one of those four edges. And we'll take a look one by one and see what happens when I do. So let's take a look. I'll copy this 4 times. Oops. Let's do this, and then we'll do one more. Okay. So, as I said, I need to be able to remove each of these or one of these edges, and so I'll remove the HF in that case, the FG here, the DG here, and then the DH here. And now what I've done when I've removed that edge is I've lowered my redundancy by 1. This is sort of the common feature that we have each time. So now we can look at these graphs and we should have a simpler problem, and indeed we do. So in this case, we can see that we have a new bridge, and we have to include that bridge. But then beyond that bridge, we have one circuit that sort of cycles through everything. All right. And so we can choose to remove any one of those edges, and we will get a spanning tree. So we can remove, I didn't count the number, 1, 2, 3, 4, 5, 6. So we can remove 4 plus 2 equaling 6, uh, 6 edges from the graph to get a spanning tree. And now why did I say 4 plus 2? Because I want to say that um, these two are sort of special edges that if we remove them, we have to be careful because if we remove those, we might bump up against these cases where we've already removed them. Okay, so those two we have to be a little bit careful when we count them. All right, great. So now let's look at, but we do have 6 more possibilities. So now we can look at this case where we've removed G and F. And for G and F, well, we've got a new bridge. This is a new bridge here. Um, and we can't remove that, but now we have the cycle here, which is again 1, 2, 3, 4, 5, 6. So I see 6 again. And again, there are these two that we have to be careful of removing. So I need to remove one of the remaining ones, but I don't want to remove HF because in this case I counted removing HF and GF. So if I've removed GF and then I remove HF again, I will have double counted it. So here I have um, exactly 5 that I can remove. So I can remove 5 here. And again, that also is going to be 4 plus 1 because we'll have to be a little careful with the other ones. So maybe I'll write it that way. 4 plus 1 equals 5. And what is the 1? The 1 is this D, DH here. That's the 1. Okay. Um, Moving on to this example, again, I've given myself one new bridge, so I have to keep that. I have, again, one cycle, and that has 6 edges. So I can remove any one of those 6. However, I have to be careful not to double count, removing HF. If I remove HF and DG, then here I've already counted removing HF and this DG. So I don't want to count that. I have to be a little careful. So I won't count that. And I'll just say again, I'm removing 5, which is equal to 4 plus 1. Great. And what is the 1? The 1 is this DH here. Great. And now we've got DH. And so let's take a look at DH. Again, I've got a bridge that I've added. And I have to look at this cycle. I've got 1, 2, 3, 4, 5, 6 again. However, when I remove these guys, I'm fine. But if I remove either one of this or this, I will have counted that in this case or this case. So these two edges I can't remove because I've already counted removing that and DH. So I only have 4 now that I can count as new spanning trees. Great. So in this case, we can count up all of the possibilities. I get that the number of spanning trees is 6 plus 5 plus 5 plus 4, which is equal to 20. So even in this case where you have redundancy 2 and you know you're only removing 2 edges, things can get more complicated than in the prior redundancy 2 case. And so you can imagine, and you would be right, that things get very complicated as you get higher redundancy and more complicated networks. All right. So I want to end this spanning tree counting exercise with another example. So let's see. I'm going to take some of these these nodes here, and let's duplicate. I'll bring this down here. So I want to do a much simpler example here and just see if we can't figure it out what's going on. Okay, so here's an example that's pretty good. So in this example, what are the number of spanning trees? Well, the number of spanning trees here is 3. And we can see that because we just need to remove any one of the 3 edges. So number of spanning trees is 3. Now let's take this same example and let's do something to it. We'll add one more vertex, um, and we will connect this vertex up to everything else. So I'll do this. So this vertex, I guess I'll call D. Now, how many spanning trees are there? Well, if you think about this, I've got 4 vertices and I've got 6 edges. And the redundancy then is 6 minus 3, which is 3. So it's more complicated from at least the redundancy perspective uh, than what we had prior. It's a good exercise. I don't want to go through it all here, but one can see if you count them that you will get actually 16 possibilities from this. Now, you might recall that these graphs that I'm drawing here have a name. Each of them have a name. So this graph is called K3. This graph is called K4. And these are the complete graphs. And so you could go up to the complete graph, Kn, and this graph is a graph with n vertices in which every 2 vertices are connected. It has the highest redundancy you can have for a simple graph with n vertices. And there is a very famous classical formula for the number of spanning trees, which says that the number of spanning trees for the complete graph with n vertices is n to the power of n minus 2. So that grows extremely fast, faster than, so to say, exponential growth. And indeed, this counting problem can be quite hard if you use the techniques that we were dealing with a moment ago. But there are some more advanced mathematical techniques, something called Kirchhoff's theorem and others that allow us to count these, well, in more generality and using some other methods. Okay,